works. The applications are all really different that you guys are going to do. One group's going to do the travel cost study, and we'll go over that on Wednesday, the theory for that. Okay, but the rest of you all need to know how to do what we're going to talk about here today. Oh, and on the papers, I've got 3 left to grade. Nearly done. I almost finished last night, but fell asleep. So, not because the papers were boring, they're actually very interesting. But we're almost, yeah. So I'm going to send them out electronically with comments. And I'll send first an email explaining kind of how to read the comments. Because there's going to be like just a row of numbers with some things next to it. And you'll understand what it looks, how to interpret that after I send out the email. Okay. All right. So the kind of the theory of hedonic, well, the name is funny first to begin with, hedonics. That sounds like hedonism, right? So people often kind of wonder where that came from. And honestly, I've been sort of looking at hedonic theory for like the better part of 20 years, and I don't really know where the name came from. There's a couple of papers from the 1930s that use this notion, but the basic idea is one that objects have like lots of attributes, and the value of an object is made up of the sum of the values of all of its characteristics or its attributes. So this is useful because the environment, the thing we talked about last time, not having a price, right? Like we talked about, you can go to Harris Teeter and get the price of an apple, and the price of an apple is going to tell you on the margin how much an apple is worth to you. You give up some other income on things to be able to buy the apple. We don't have that for clean air, but clean air is going to be a characteristic of certain things that we do buy. And the biggest one is going to be a house, okay? And we tend to think as economists that people put a fair amount of effort into thinking about buying a house more than they maybe put into thinking about buying an apple, right? So we ought to think that maybe they're going to, do a little bit of research and express their true value for the characteristics of houses. And from that, if we're careful, we can peel off the value that they put on each individual piece. So that would include like the number of bedrooms and bathrooms, but it will also include surely things like school quality, crime rates, and then eventually you get down to things like air quality and water quality and stuff like that. Okay. Generally, as an environmental economist primarily, I tend to focus on the air quality part or the water quality part that we'll talk about a little bit later today. I'll go and give talks in audiences of non-environmental economists, and they'll tell me that, when I bought my house, I didn't think at all about the environmental attributes. I thought about the school quality mainly, right? And as somebody who's bought houses with kids, I tended to mostly think about school quality too. That's the thing, I think, first and foremost in everybody's mind. And then you look around and you think about whether there's crimes occurring on the street corner, right, and whether that's going to be a problem or not. And the point I guess I'm trying to get at is you get all the characteristics of a house lined up, and if you're very careful about how you control for the first 9 or 10 of them, the 11th one might be air quality, and you can back out people's value for air quality from the decisions they make about which house to buy. Okay? If you're not careful about the first 10 things people care about more, then you're going to get a misattributed value to the air quality part. Okay? And this is sort of why I like to give these projects out and why you're going to work on real data, is because you're going to find that depending upon what you put into the regression with the air quality, you're going to get dramatically different numbers, like numbers all over the place. Air quality might be good, it might be bad, it might be really, really good, right? It might be horrible. All depends on what you put in with it. So I want to give you a sense of just how hard it is to kind of do this sort of thing well in the real world, and that's why you guys will use the real data and mess around with it. So the first paper that ever tried to use this characteristics theory of value to sort of get at the environmental attributes of housing was this paper by two guys, Riddicker and Henning, back in the 60s. And they looked at sulfur dioxide sulfates in St. Louis. Okay, and they found that people, generally don't like bad air quality, But there wasn't much theory in that paper. They found that houses that had bad air quality sold for less. And it kind of made sense. It wasn't until the 70s, and this guy Sherwin Rosen at the University of Chicago, who died, I think, now we're about 15, 16 years out since he died. When he died, the whole industry of hedonic analysis kind of took on a new life because people started having conferences in memorial of Sherwin Rosen. And those conferences got a lot of smart people to get together and think about how to do the sorts of stuff we're going to talk about today. And you had this whole new kickstart to this like empirical industry that had been kind of petering out in the 80s and the 90s. But his paper back in 1974 is kind of like the one that started it all. Because it took empirical micro theory, an empirical micro, but just in general micro theory, and attached it to the data, the empirical analysis that the guys studying St. Louis were doing. Okay? So this is the paper that every paper I write basically references Rosen to start with. So he gets a lot of citations out of me. He's not around anymore, but his citation count piles up because a lot of people use his theory. Okay, so what we're going to do is focus on the Rosen theory and how it works in practice. We're going to do it in a housing market context. You could do this with other things. The first paper I think I ever saw that used hedonic theory used it to study the attributes of cars. And the idea was to figure out like how much is another door worth. And they studied cars back in like the 1950s, and they found like another door is worth $200 or something, which doesn't strike me as a very interesting thing to do, right? But you can use that. You can use any product that has lots of characteristics to value the characteristics. We're going to focus on housing, because once you control for neighborhood characteristics, crime rate, school quality, stuff like that, site characteristics, like how big it is, how big the acreage of the plot is, how many bedrooms, how many bathrooms, stuff like that, we can back out lots of interesting things about environmental quality. So as you start to do this, you got to keep in mind, you'll start to get a sense of how these things work. But for instance, once you've controlled for how big a house is, you might think that having, say, more bedrooms would always be a good thing, or more bathrooms would always be a good thing. Conditional on a house being a certain size, more bathrooms is always good, but more bedrooms actually starts to become a bad thing, right? So if you think you got a 2,500 square foot house and it has like 4 bedrooms in it, that's kind of a nice normal sized house and it would look pretty nice. But if you have a 2,500 square foot house with 10 bedrooms in it, that's like a weird development that somebody put together, probably because they're like housing a bunch of, no offense, but grad students and like lots of confined, they're trying to pack them all in, right? So in general, you get a lot of sort of confusing relationships between variables when you start to control for lots of house characteristics. And we're going to have to see how that all works, and you guys are going to stick those things into your regressions and discover sort of how confusing these things can get. All right. So when you go and run a hedonic regression, you're basically going to recover a function that looks like this. Okay? So the dependent variable in that regression is basically always going to be the price of a house. Okay? Frequently you'll use the log of the price of the house, because if you put the log of the price on the left-hand side, the things on the right-hand side tell you percent changes in house values. So like one more bedroom raises the house value by 4%, as opposed to $800. Okay? Hedonic regressions tend to fit better in percentage terms. Things generally push up the value by percentages, not by fixed amounts. I'll just kind of tell you that from lots of experience. Yeah?
So how do you order the characteristics? Is it just saying Z1?
Yeah, okay. So this is the notation I'm going to use here, because it's, we can't really draw something with multiple dimensions. It's just a pain. So I'm going to talk about the function being drawn in the dimension of one of these variables, Z1. And you could think about, because this is an environmental class, think about Z1 as being air quality, or Z1 is better air quality. Z01 is everything else about the house. So that's like a vector that includes square footage, bathrooms, bedrooms, crime rate, everything. Okay? And it doesn't really matter, how they're ordered in the regression. It'll come out the same way either particular way, but when we draw it, we're going to usually draw it one dimension, holding everything else fixed. Okay? So if you run a multivariate regression of log price on air quality and everything else, if I don't interact air quality with the other things, then I can just draw this line for any value of the other things. It won't really matter what they are, right? Okay. And you can see I made it not a straight line. So maybe I have Z1 and Z1 squared in that regression, for instance. Okay? All right, so yeah, we're gonna have a big vector of characteristics that, you know, environmental quality will be one, and yeah, we'll just say Z1 is the air quality part. Okay, so economists will talk about implicit prices, all right? And this is just a lot of notation, but essentially all we're doing there is taking the derivative of that function that we estimated with respect to air quality, okay? So if it was just log of price regressed on air quality, then the derivative of price with respect to air quality, you'd have to use the logarithmic derivative formula that we talked about in that day when we did Stata in this classroom, like really early in the semester. If you just regress plain price on air quality, then this would just be a constant number, right? Just a linear function. But whatever it is, what that number tells you is how much you have to give up in other stuff. And, you know, by paying more for a house, you're giving up money that you could buy food with, or that you could go to movies with, or you could take trips with. How much of that other stuff are you giving up in exchange for one more unit of Z, Z1, right? That's what the slope of that line is telling you at the margin. So if we take that derivative and plot it, you know, here it's an increasing function, so the derivative is positive, but it's getting smaller as we go up. So we plot that, and basically what we have is something that looks a lot like a demand curve. So you're willing to give up a lot of other things in exchange for one unit of Z, or Z1. But by the time you've got a lot of Z1, you're not willing to give up very much to get more. Yeah?
How is implicit price different from like marginal cost?
Well, I mean, it's sort of like the marginal cost of the house, right? That you're paying a little bit more on the margin to get a house with nicer attributes. So to that extent, they're the same. But you're not producing a house. Usually when we talk about cost functions, it's like I'm making output, and these are the costs that go into it. This is sort of more like a demand curve, where it's kind of like the marginal benefit I get from an additional unit of air quality is what I'm willing to pay for it. But now you're not going to the air store to buy more air, you're going to the housing market, and you're paying a little bit more for this attribute of the house, right? That's the only difference between like a regular grocery store and the housing market, okay? So I still haven't really introduced any economic theory, but the idea hopefully kind of makes sense, that you're willing to pay a little bit more for a house. Here you're willing to pay quite a bit more to get nicer air when your air is horrible, and when your air is pretty good, you're not willing to pay that much more. All right, so it's a diminishing marginal utility of nicer air. So here's a couple of actual hedonic price functions, and the implicit price function, the derivative that came off of that from a paper about the Superfund site that we talked about once or twice in Massachusetts, Woburn, the place where the John Travolta movie was made about. So there's got the movie poster in there, and there's a little story about it. It's actually true. I mean, it's based on a true story, although they got John Travolta to play the lawyer. The lawyer's probably not so much John Travolta. But this is an actual hedonic price function from that data set, where the amenity we're talking about is how many miles away from this particular Superfund site the house is located. So you can kind of expect, as you would expect to see, the house prices get higher the further miles away you are from the Woburn Superfund site. So they start off around 150,000, right, and work their way up to 200,000, kind of asymptote. And if you take the derivative of that thing and plot it, right, you're willing to pay close to $50,000 to get that first mile of distance away from the Superfund site. And by the time you get out to 3 or 4 or 5 miles, it doesn't really matter that much anymore. Prices aren't going up by very much, right? So to get this number, you'd have to control for a lot of other things, because certainly there's other features of the houses that are different, right? If you consider houses that are close to the Superfund site and ones that are further away. And generally the way the world works is the houses close to the Superfund sites tend to not be the very nice houses, and the ones further away tend to be nicer. And that has to do with reasons that, you know, go back to the fact that they built the Superfund, well, they built the leather plant that became the Superfund site in the place where housing property values were low because land was cheap. So the houses that are here were kind of smaller and not as nice before they built the thing, and now they're the ones that are close to it afterwards. So if you don't control for that, what you end up with is the model would tell you that the effect of the Superfund site is really big, right? Because it's saying the houses here are super cheap and the ones out here are really expensive. But part of the reason that they're so cheap in here isn't because of the Superfund site, it's a reverse causality story. Yeah?
So in a regression, how would you control for that?
Well, I mean, the easiest thing there to do would be to put in the house attributes. So like square footage is probably a lot smaller in the houses in here than it is out here. That's the easy part, right? The problem is that there's other things about the houses in here that are not in your data set. And there you need to be creative, or maybe, you know, that you don't always have an answer. It depends a lot on the data set that you have available. Okay, so that's sort of the, you know, that's an example of this in practice. And you can kind of see in, you know, in spirit at least, how you would take those numbers and convert them into some sort of like measure of welfare, or its willingness to pay measure. But we haven't talked about utility functions yet. And what Rosen, 1974, gets you is a connection of those functions that I just described to utility functions, which is useful because that's going to let us put specific welfare measures like compensating variation in income, right, which is one of the ways that we would define you know, the effect of a price change in intermediate micro. Now we can attach that to the hedonic model. Or, I mean, if you remember it better, we can come up with a measure that's basically consumer surplus. Okay? So things that have sort of measures of value that we can put into a cost-benefit analysis. Okay. So we're going to write down this utility function, and it's going to have three things in it. And just to give you sort of the sense of where it's all going before we start moving the utility functions around and making indifference curves out of it. Z is our vector of all the house attributes again. So Z1 can still be air quality and everything else, Z2 up through ZK. X is everything else that you could buy. So just think about X as being like a big basket of all the other things you could consume. So food, shelter, well not shelter, so we're going to talk about buying a house, but clothing, entertainment, okay, just whatever else you're going to spend money on. The reason we have to have that in there is because you need something that hurts you when you buy a nicer house. You need a reason why you don't just go buy the biggest mansion in the cleanest neighborhood with the best schools every time, right? And the reason has to be because there's something else that you're going to get less of if you go spend all of your income on a really nice house. So that's the other stuff right there. I'm gonna index people's preferences by alpha. Now this gets kind of like, this is a notational sort of thing. Economists will do this all the time, where they'll say, we put it after the semicolon to say it's not a variable, it's not something you're consuming, but this is sort of the index of who you are. So this could be education, or it could be age, or it could be whether you have kids or not, okay? All the characteristics that might make your preferences for clean air go up or down are summarized in that one particular, in this case, Greek letter. All right? And we're also going to have income, because we're going to have a budget constraint. That's really important. Yeah?
So when you say characteristics of households, you mean people in the households, not the actual homes?
Yeah.
Oh.
Yeah. So that's a good point. I'm going to try to be consistent in my wording, and I'll probably slip up. But usually we talk about households as the people who are in the house.
Okay.
And then we talk about homes, like specifically homes as the actual physical structure. And in hedonics, they're very importantly different things because, right, the homes, the people are the ones with the preferences and they're choosing over the homes. Yeah. All right, so this is the only time really this whole semester you're going to see multivariate calculus, not in a really complex way either. But the way to sort of take the individual's utility maximization problem and convert it into a welfare measure just requires a little bit of Lagrange theory, okay? So up top, what I've got is the utility maximization problem. So the individual is going to choose a house, which means a combination of Z. And that's going to leave them with a certain amount of X that they can consume, right? Because they have a budget constraint, which is that what they spend on their house minus, or in addition to what they spend on everything else, adds up to income. So we're not talking about savings, but you can do this in a dynamic model if you really wanted to, and have people putting money aside and saving it for the future. The price part here is just going to be the purchase value. So the data sets that I've given you, if you have a hedonic data set, has in it a house price, like a purchased house price. So that abstracts away from a lot of stuff about mortgages, which people do think about now and then. And if you do work on housing over the course of the last 15 years, which kind of is where a lot of our data are right now, then modeling the mortgage is actually really important, right? Because we had this big problem in the mid-noughts with people getting like really, really cheap mortgages for houses they couldn't afford, and then all of a sudden like the house prices dropped and then they couldn't pay their mortgages anymore. So that's kind of going to be ignored in the way you guys run your estimation. I don't think any of the data that I give you has details about the mortgages in them. But, so, you know, we'll still get useful results out of the data. If you take the first order conditions associated with that Lagrange expression, right, we've got, with respect to the house attributes, each one, or just take a particular one, air quality. We've got the marginal utility of air quality. We've got the Lagrange multiplier. What's an interpretation of the Lagrange multiplier in a utility maximization problem? You remember? Yep.
Constraint function.
Well, it's the shadow price on the constraint. That's right. But it has an economic interpretation too. What does it mean in this case to relax the constraint? Okay. If I give you a little bit more income, then that's relaxing the constraint, and it means that you can now optimize that additional income over how you consume Z and X. So what's the way that you would think about lambda now has a name if you think about what I just described? Yeah? Well, it's the shadow price on your budget. So it's the marginal utility that you get from a tiny bit more income. So in economics, we talk about it as the marginal utility of income term, which turns out to be really, really important in almost everything we do in environmental economics when you do benefit stuff. Because what we're going to see at the end is that we're going to take the marginal utility of income, lambda, okay, and we're going to divide the marginal utility that we get from better air quality by the marginal utility of income. And that's, in a sense, going to monetize our preferences, okay? So here's one more intermediate micro question, and then we'll stop with that for a while. What's the interpretation you could give to that ratio of two different marginal utilities? We kind of talked about this last class, yeah. Exactly, right? So this is the marginal rate of substitution between air quality and other things, which if you go back to an indifference curve graph, that tells me how much other things I'm willing to give up in exchange for a little bit more Z and hold my utility fixed. Which is what we said last class was sort of the way you think about willingness to pay for Z. Okay? And if this was apples at Harris Teeter, then that willingness to pay would be equal to the price of apples. But here we don't have price of apples, right? Because we don't have price of air quality because it's not marketed in a store. But the theory here, if I take these two first order conditions, I take this part over to this side, I take this over to that side, I take the ratio of those two marginal utilities, lo and behold, that marginal rate of substitution turns out to be equal to the derivative of that hedonic price function with respect to Z, right? So what Rosen figured out was that if we take that, if we run the regression that the guys in St. Louis ran for air sulfates, we take the derivative of that thing with respect to air sulfate, that's going to tell us the marginal rate of substitution between that thing and other stuff, all right? So this gives us now a way to like formally talk about the benefits people get from an additional unit of clean air. Yes.
Just a clarification question about the notation. So
Yeah.
X and the P's, are they the same thing?
X and PZ, you said?
Yeah.
So PZ is the price of a house with attribute Z. Okay? And Z is a vector. I think in earlier notation, sometimes we put like bars underneath variables to say that they're really like a whole vector of lots of variables. So this is the price of a house with 2,000 square feet, 4 bedrooms, 3 bathrooms, mediocre schools, and bad crime. Okay, that's like the summed up in that. And X is everything else you spend your money on besides the house.
So in the last line of this slide, we
Yeah.
substitute the like how did we get from the left-hand side to the right-hand side? The last line.
How do we get from there to there?
Yeah.
So if you take the ratio, so I skipped a couple lines of math here, but if I take this term over to that side, I have the marginal utility of better air is equal to the marginal utility of income times the derivative, right? That's if I take that over. And here I've got the marginal utility of additional consumption of all other things is equal to the marginal utility of income. Okay? So now if I take the ratio of that divided by that, I have the ratio of that divided by that, and the marginal utility of income part drops out, and I'm just left with the derivative of price. Okay? Yeah. So yeah, sorry, I left a few lines of the math out of there. Okay, so that's it in Lagrange form, but we can also talk about this in graphical form. And sometimes I think it's easier to see it as a picture rather than as a Lagrangian. Okay. And when Rosen did this, his paper does this with lots of graphs. He kind of confuses the whole question. I think he confuses a lot of students and me for many years trying to figure this stuff out. By instead of calling an indifference curve an indifference curve, he calls it a PID function. Okay? Which really kind of tells you the same thing in the end, but I'm going to call it and talk about it more as an indifference curve, but I'll show you kind of how they mean the same thing. So if you think about the level of utility, U0, just some given level of utility, all the combinations of Z and X for a given person with attributes alpha that would yield that level of utility, that's going to be an indifference curve. Okay? When Rosen does it, instead what he says is, what's the maximum somebody would be willing to pay in terms of a house to get a house with attribute Z when their income is Y, their preferences are alpha, and the utility they're getting is U0. Okay, those two things basically mean the same thing. And if we look at it in a picture, okay, Rosen is talking about the maximum somebody would be willing to pay for a house with these attributes if this is their income and that's their utility. Or alternatively, you can just think about this as all the combinations of house attributes and other consumption. But here the other consumption is your income minus the price you're paying for the house. Okay? So it's what's left over. The house is, yeah.
So just generally speaking, how come people are so, because the indifference curve kind of varies a lot on the y-axis, like it stretches a good amount, like
that?
Are people that flexible with like the price of houses? Because usually I feel like people set a budget and just kind of purchase near the budget, that seems like a big spread. For like,
yeah, well, I mean, I guess the point would be is that you set your budget and then you go purchase the house that's at the, you say, I'm going to spend this much, and you're either looking for a house with certain attributes, or you're saying, I'm going to spend this much, but in practice, you probably have in the back of your mind both things.
Yeah.
Right? And then you actually are only ever going to use the point where it intersects on the budget constraint.
Right.
So I'm going to buy this house that costs this much and has that air quality, but I might be willing to get more air quality at a higher price, but maybe I'm really not willing to pay very much to get that. Right? If I offered you, I'm going to ratchet up your air quality by 20%, but I'm going to charge you another $10,000, would you pay it or not? Right? That's going from the point where you actually buy, which is where your indifference curve touches the budget constraint, up along your indifference curve, right, and asking if you'd be indifferent between those things. Generally speaking, the only thing we ever see is the point where the person actually bought the house, because we don't usually see them buy multiple houses, right? You don't go to the store every week and buy a new house. And just to be clear on sort of how these indifference curves, combinations of house price and air quality work, which direction would be better? Indifference curves are level curves of a three-dimensional function. Which direction has the higher function on that graph? If I was to plot the three-dimensional graph over top of it, give me a compass direction that describes the higher, yeah. Up in that direction?
Yeah.
This should actually so as we move up in this direction, we get more of a good thing and more of a bad thing. So utilities should kind of stay fixed. Yeah? Yes, right? So this is a bad thing. Higher house price is something we'd like to avoid. Air quality is a good thing. So if we can move down in this direction, we get more air quality and less expensive house, we would take it. You could get the biggest mansion with the best air quality for a really low price, that would be really good. Really expensive house with bad air quality is bad, right? So this is the direction that you're trying to go. So if this is your budget constraint, this is the set of houses that are out there. You're trying to get on the highest indifference curve you can get to, which in this case is this one. Okay? So you've kind of seen utility maximization before. Usually what it has is X and Y. And the budget constraint in that graph usually goes this way, because X and Y are both good things. Here we have one thing that's bad, more money spent on a house, and one thing that's good. And when you have a good and a bad, the budget constraint goes from southwest to northeast. So you gotta get your head around that. If you have a bad thing down there, then you have two bads, and the budget constraint looks just like the XY that you see in intermediate micro, except there the better bundles are the ones closer to the origin. So you have to always be thinking which direction is the good direction. Okay. So we're basically trying to recover people's preferences, the shape of their indifference curve, by the slope of their indifference curve, their marginal rate of substitution, by looking at the slope of the price function that they're optimizing with respect to. That's the same thing we just talked about in Lagrange form, but with a picture, okay? And that's what you're gonna go ahead and estimate. Now you can do this with multiple kinds of people. And for the most part, what I've got you all set up to do when you do this in the projects is gonna ignore heterogeneity. Heterogeneity, this is where the household part starts to come in, the difference between households and houses. Because I could have two different kinds of people here, individual B and individual A. And individual B here has steeper preferences. No, I'm sorry, I guess this is a concave and hedonic price functions. They have flatter preferences, but the way that lines up, it has them choosing a spot with a higher level of Z. They're optimizing out here, whereas type A individuals optimize at a lower level of Z. Okay, so that's just doing the utility maximization problem with different kinds of indifference curves. But the problem that you run into when you try to do this in practice is that you only ever see each kind of person by one house. So if I'm trying to recover what their entire, different people's indifference curves look like, right? I can't take two different people and say that they're two individuals on the same indifference curve if I know that they have different preferences. They're going to look very different. They're going to have different shaped indifference curves, all right? So I'm only bringing this up because you're not going to have to do this. You're going to basically estimate one value for everyone. And the reason that's really hard is because how do you back out sort of the shape of different indifference curves when you only see people by one house? This is actually what we spend most of the time in my graduate class studying. So next spring, Luke's going to be in my graduate class where we do this. And he's going to have to then figure out how to recover basically the shapes of those two different indifference curves when you don't necessarily see people multiple times. And this is what people have been working a lot on since Sherwin-Rosen died in 2002. So really complicated papers and methods. Okay, so I'm only saying this because there's like a part of it that you don't have to learn and you don't have to see, and I kind of want you to know where the boundaries are. Okay. So, and in a minute now, I'm going to show you some examples of easy models, like the ones you're going to run, so that you have a sense of how these things work in practice. Okay. So to summarize it all, the hedonic price function is going to show us how the house price is going to vary with the attributes. Okay, and that's, you have to use multiple regression, multivariate regression, to control for some things while you're trying to back out the value of other things. And unfortunately, usually what we're dealing with is a trade-off between putting in too many variables in the regression. And if you have too many variables that all look the same in a regression, what problem is that? Somebody who took econometrics, I know like half of you or more did. So you have lots of variables that basically, from the point of view of data, do the same thing.
Perfect collinearity.
Yeah, multi-collinearity or perfect collinearity, and you've got a really bad problem. That's on the one hand as you put more things in, and the flip side is that if you don't put enough things in, what's the other problem you're going to run into? Omitted variable bias. So, like, I spent all my life going back and forth between dumping more variables in, trying to avoid the omitted variable bias, and then suffering from collinearity problems. Every project, that's all it is like trying to decipher which variables should actually be in there. Okay? And just to give you a sense of like the reality of it is that you can very easily spend your time trying to pick out the right combination of variables that give you the answer you want. And you'll see this when you go and run your projects, the people who are doing hedonics. You can mess around with what variables to include and try to get the value of brownfield cleanup or Superfund cleanup or air quality to get bigger and bigger and bigger. That's like there's people talk about you can rig statistics to show whatever you want. Right? This is a classic example of where you can get away with that. So if you want to be an ethical researcher, you should sit down at the beginning and say, these are the variables that I think matter, and I'm going to go with them. And if they tell me that air quality doesn't matter, I'm going to go ahead and try to publish that. And I'd say good luck trying to publish that, because nobody will ever take that paper. But you know that would be the ethical thing to do. Yeah.
So what does multi-collinearity actually do to your regression results? And does it make any sense?
So practically, if you have multi-collinearity, what's it going to look? Can anybody tell me what it'll look like? Yeah.
You have to omit a variable that is.
Well, that's if it's perfect. Yeah.
Oh.
If it's perfect multi-collinearity, Stata won't even do it. It'll just say your regression is bad, right? And give you lots of like zeros or something. But if it's sort of, it's usually not that bad, right? Usually we don't have two variables that are exactly the same. So if they're just very close.
You have super high standard errors.
Yeah, generally your standard errors kind of blow up, and you get signs that sometimes look crazy. Okay. So you're throwing more and more variables in, and then all of a sudden you start to see all the things that made sense in your regression now kind of like look like garbage. Lots of big standard errors and signs that just like are nonsensical. So then you'll take a few things out and you'll put a few things back in and play around with it for an hour. Yeah.
When you say the signs are like crazy, you're just talking about something you thought had like a positive relationship is now negative.
Yeah, I mean we go into these things with priors. Right, and then when I talk about signs making sense, intuitive signs, it's usually do they match your priors? And there's again like a big risk, right? Some things we kind of have a pretty good prior, square footage should be positive. And there's like enough studies that we kind of even know what the range of square footage value should be. In New York, the square value of another square foot is very different from the value of a square foot in Durham. But then if I talk about school quality, well that should probably be positive too. But what if I start to talk about like, I don't know, you can get into other variables where it's not 100% obvious, right? And it's not always just that the sign is wrong too, but the, it might be very big or very small. It just doesn't cross the zero threshold, right? But maybe it's too low relative to what it should be. Yeah. So there's a lot of that in what we're gonna. It's more of an art form than it is a science. Coming up with how to specify your hedonic regression. So the slope is going to tell us the slope of the indifference curve based on the graphs and pictures that we just showed, and that's the marginal willingness to pay. If we go back to the Lagrange formula, your willingness to give up a little bit of other consumption in exchange for one more unit of whatever the good thing is, right? Holding your utility fixed. All right. So I want to give you an example, because maybe this is a little too abstract, and an example might bring it home a little bit. So this is actually now, I stick with the working paper version because I had nice graphs to show you, but this is actually a paper that we published in 2015 in the AER on shale gas. Okay, and in particular, on the outcome is basically the same in the working paper and the published paper, just so we have better data in the published paper. Essentially what we're looking at is, there's a lot of externalities from living next to a shale well. A lot of things that the gas company doesn't have to pay for, that you pay for essentially as a resident living with one of these things in your backyard. And in particular, we were interested in the effects on local water supply. So there's a lot of concern that a lot of shale wells are going to start to fail, and people are worried that their house will lose all its value if the water source that they have for the house, the groundwater that they pull out to drink, all of a sudden becomes contaminated with this list of 600 chemicals that they put in the fracking solution. If you're on city water, people worry a lot less about that, right? Because there your water is coming from a treatment plant. You don't think it's such a big deal to live next to a shale well. Interestingly, I'm going to talk about the effects on groundwater and the value of the house if it's groundwater dependent. But I have a grad student who's at the University of Kentucky now, who just finished a paper with another person I know at the University of Rochester. And they found that if you live in a place where your city gets its water from an intake that's within 1 or 2 kilometers of a shale well, your infant mortality risk, if you're a pregnant mother, doubles. Because there's actually fracking chemicals in a lot of the water that cities provide to houses if they're getting their water from places that are close to where the shale wells are. They use data from Pennsylvania for that. Okay? So I'm going to talk about groundwater contamination, but it's actually now looking like shale gas is the risk for piped water to seawater. Okay. So the problem, the thing that makes this a difficult thing to do, in principle here, is that there's a lot of things, omitted variables, that are going to be correlated with the risk of contamination to your groundwater. One of the big ones is going to be houses that are close to shale wells generally also tend to get lease payments. So when they come to get to offer you, when they come to lease your land to drill on, they say we're going to pay you usually between 12 and 20% of the revenue that we get from selling the gas every time we sell some. Okay? So that can be like 6 figures, 7 figures over the span of a well if you're lucky. So it can be a lot of money, right? And if the lease payment, if it sticks with the house, then the house value will go up, right? Some places will let you actually take the lease payments with you when you sell the house. You can split the lease, you can split the mineral estate from the surface estate is what they call it. That's something we're really interested in too. The other thing that happens that you have to take into account is there's a lot of demand for housing in places where lots of well workers are moving in. So probably nobody here has ever been to Williston, North Dakota, right? It's an interesting place to drive through if you ever have the opportunity. So I was driving back from Montana the summer before this last one, and I toured and went up through Williston. And you know what you pay for a smoothie in Williston? It's like, pineapple, mango, and yogurt. Let me take a guess. That big. $18 for a smoothie in Williston, right? So I'm talking about the housing demand, and prices for housing goes up, but the prices of everything goes up when it's in short supply. I mean, I was happy to pay that because it gives me a good story to tell, but generally you feel pretty screwed if you're paying $18 for a smoothie. But you want to sort of account for the fact that prices are rising for everything in this area because there's a lot of demand in places where there was nothing happening before. Okay. Then the other thing is a lot like what I was just describing with the Superfund site. They tend to put the wells in places that aren't random. And this is particularly true in Pennsylvania, where they'll look for houses that are cheaper, where the land is cheaper, and they can come in and offer the owner less to build a well pad on their property. So you'll oftentimes see, the houses are not, it's not a random allocation of wells across houses. They might be next to the good houses or next to the bad houses. Okay, so if you go and you run your first simple regression, the easiest thing you could do would be to regress price on, say, the distance to a well pad, okay? And then on other house attributes and an error term. right? This would be kind of, you know, the simplest thing you could stick in this data. And in a minute, I'll show you what you get when you do that with the shale gas data. But here's the problem that you could run into, right? So if you've taken econometrics, you'll think about looking at the correlation between regressors and the error term should kind of ring a bell. That's a problem if that's not 0. If you haven't had econometrics, what you want to think about is just Stata is a stupid machine. It doesn't have a brain, right? It can't think. And if you give it a variable that looks a lot like the error term moves with the variable, Stata is just going to like attribute the error term to the variable. So if the variable is always big and the error term is always small, Stata is going to drag down the value, like the effect of that variable. So it's going to attribute what's happening with the error term to the regressor. And the opposite could be true too, okay? That's like omitted variable bias, like in intuitive terms. So here we've got two things to worry about. The further you get away from a well, the lower the house value might get because you're less likely to have a lease. Like if you're close, then you're more likely to have a lease and the value of the house might be a lot higher. So here the lease payment is actually in the error term. It's really, really hard to get lease payment data. Well, that's something we've been working on actually putting together. We have to like scrape text files off the internet, like 300,000 text files, and turn them into text and then scrape it using Python. Like that's how you get that kind of data. I can't remember the group doing the fracking. You guys know. You guys may actually have some of that scraped data. I can't remember what you're going to use. And then if the wells are next to the like rundown houses, then the correlation would be positive. The houses further away would have a higher value. Okay, but either one of these things would create a bias. So the first thing that we usually talk about doing is putting in house fixed effects. So you're in luck if you can see the same house more than once. Okay, that's going to help with the problem that houses might be different in unobservable ways, because now what I can do is put in a dummy variable that basically turns on if it's that particular house. Okay, so you guys saw what that did in the exercise that we did in earlier in the semester with the shipments of toxic waste, hazardous waste across states, right? Putting in the state dummies actually solved a lot of problems because states had like, they were good or bad as receptors of waste. We said like Nevada might be a really good receptor of waste for reasons that we can't see. So the Nevada state fixed effect controlled for a lot. Well, here you can do that with individual houses, all right? That gets tricky when you have, you know, say 10 or 20 or 30,000 houses and you want to put in a fixed effect for every one. You're not going to do a matrix of fixed effect like variables like we did for the thing we did earlier in the semester. So what we do generally there is we take differences. Okay? So if you think about what this regression up here looked like, if I've got the price of the house in period t, and then I've also got it in period t minus 1, that could be like the year 1997 and 2003, or take any pair of years, and I take those differences across the two periods, the fixed effect is the same in both periods, so it drops out, right? And now what I'm doing is I'm regressing the difference in the house price on the difference in the well distance, which actually then requires that over the period when I see the house sell twice, something changes about the well exposure. Yeah.
So can you just re-explain the dummy that you added, the fixed effects one?
Yeah. So do you guys remember basically how the dummies worked in the exercise we did in class? This is basically mu is the dummy for every house.
But like how? In what sense? Like what is a dummy? Like when
Yeah.
is it 0? When is it 1? I didn't understand.
Yeah. So the dummy variable is 0 or 1, but it's like a variable that has a coefficient on it for every house. So essentially what I'm saying is like, you know, you can take my house in Chapel Hill and I might see it sell twice. We bought it in 2004, and if I sell it again in 5 years, you'll see two prices on it, and everything about that house that's the same over time is going to get summed up in like one variable. Maybe like $130,000 worth of the house value gets captured by that fixed effect. And the other stuff is the stuff that changes, right? Yeah. So if I take the differences, I knock that thing out, and now I'm running a regression in differences, and life is easy again. Because I don't have to build a matrix that's got 30,000 fixed effects in it. But you do have to see the actual change over time in well distance, which happens if they build a new well. It goes from being like, the well distance could start out as infinite, and then it goes to like, 800 feet if they build it in your backyard. Okay? So here's what happens when you actually do this in practice. If we use the inverse distance to the well, it's more convenient to use the inverse distance because inverse distance, which is like proximity, right, can be a lot, well, if distance is infinite to begin with, then it's 0 when we're talking about 1 over distance, which is a lot easier to talk about when there is no well there, right? So if you start off doing simple OLS without house fixed effects, you actually get a number that says that the inverse distance or the proximity is a good thing for houses, okay? And this is houses that could be on groundwater or not on groundwater. In general, having a well nearby is a good thing, which is probably capturing the fact that those houses are all getting big fat lease checks, royalty payments, okay? Then in addition to distance, inverse distance to the well, we put in that variable multiplied by whether the house is on groundwater or not. So if I have a groundwater house, what I would do is take the effect of the inverse distance and I would add to it this additional coefficient. That would be for a groundwater dependent house. Yeah, was there a question?
Could you not use the well yield as a somewhat of a substitute for lease payment, based on the idea that what they would pay for a lease is like a valuation of how much they're spending there?
Yeah, I mean, so the only problem with that is that you have houses where the lease payment was split from the house sometime in the past. So right now, the owner of the minerals might like live in Florida and be getting the check sent there, whereas the people in Pennsylvania actually have the well in their backyard, but they don't get any payment for it. Because 30 years ago, the guy took the mineral rights when he moved to Florida with him. And it's very, very hard to see when the lease is split, when the mineral rights are split from the house. To do that, you have to scrape lots of text from big legal documents that have like, bad photocopy marks on them and stuff. It's complicated. And the splitting of the royalties off from the house is actually really common in Pennsylvania. Because like 100 years ago, they had a lot of oil drilling there, 150 years ago. So since that time, people, when they moved, said, oh, this might be valuable for something in the future, somebody keep the mineral rights. Yeah.
A follow-up question to that is, these lease contracts, are they, like, if they are for a longer time, then would you also expect the drillers to be anticipating a lot more coming out of the well, so they could use like the lease duration?
Yeah, I mean, usually once you've started to drill, the duration is until they're done.
Oh, okay, fine.
Usually the way the lease works is you get either up to 3 years or up to 5 years to start drilling, and if you don't drill within that term, 3 or 5 years, then the lease reverts back to the homeowner. So usually what they do is, the day before the lease reverts back, if they don't want to drill yet because oil prices are really low, they come in and drill a dry hole in the ground, and then now they have as much time as they want. But they don't actually have to start pumping anything. So what we find is that when we do the fixed effect analysis, so we put in the characteristics of the house are captured in that fixed effect, now all of a sudden you still get a positive effect if you're close to the well because of leases, but now there's a statistically significant negative effect on top of that if you're a house with groundwater. Okay? And if you wanted to know the net effect on a groundwater house, you would take the effect on all houses piped in groundwater, and you would add to it the effect specific to groundwater houses, and you can see that the negative part is always bigger than the positive part. So if you're a groundwater house, then having a well very nearby is a bad thing, a net bad thing, okay? Whereas if you're a piped water house, it's a good thing. That's the way to read those regression results, all right? So we wanted to do something that was a little more rigorous, and I think one of the groups has got a diff and diff experiment built into what I suggest you do, okay? And this is basically how difference in differences work. So this is what economists call these quasi-experimental methods. Quasi-experimental meaning that what you're trying to do is replicate something that pharmaceutical companies do when they do random drug tests. and they do experiments, okay? So what you do is you set up a treatment group, and the treatment group is the group that actually gets hit with something. And then you set up a control group who looks like the treatment group in every way except they don't get hit with the treatment, okay? And the idea is that the control group tells you how the treatment group would have behaved had they not gotten hit with the treatment. And I'm going to define what treatment is in just a second. I'm being intentionally vague about that for now, okay? So in a drug trial, the control group is a randomly selected group of people, and the treatment group is a randomly selected group of people, and you could say because they're random, if you didn't give the treatment to the treatment group, they would come out the same as the control group. But then we hit them with the drug, right? And then see what happens. Here we don't have that luxury because we can't randomize where the wells go. We have to sort of live with what actually happened in the data. So here's a picture. I apologize. This is a lot of my graduate class notes are actually hand-drawn using various apps. And this is what I pulled from one of my graduate classes. So this is a picture to tell you how difference in differences works. And then I'm going to show you the results, what you get when you do difference in differences with the shale gas. So we've got our control, okay, I'll tell you exactly what the control houses are in a minute. And over time, the houses in the control group might be getting more valuable just because, you know, this is maybe the run-up in the housing market in the previous decade or something. And then we've got the treatment, and in the treatment, we start low and we go high. But what we're going to say is that in the absence of the treatment actually hitting the house in the middle, here it's a positive thing the way I've drawn it, the two things would have behaved the same way. So these are parallel and these are parallel, and it's just that there's a break somewhere in the middle coming from the treatment. So if I take 2 points in time, T0 and T1, and I look at my control group and how the price goes up there, I've got that labeled by A. And then I take the treatment group and I look at how its price goes up from T0 to T1, and I label that as B. If I take B minus A, and you think about it and stare at it for a second, B minus A is going to be that difference right there. If these things are the same and these things are the same, except for the fact that we shifted that up. Okay? Yeah?
So why is is A usually smaller than how it looks on this graph? Like, is it usually much closer to the black line, to the red line?
It doesn't really matter, right? I mean, you could end up with any sort of, you know, A is the difference between these 2 points right here, and it's just how much did the control group improve over time.
Oh, sorry, I meant to say, I thought A was the difference between the two.
Yeah, no, they're drawn kind of close together, but that's completely, the control group can be way down here and the treatment group can be way up there.
But then, sorry, the way I'm trying to phrase the question is more that if the groups are supposed to behave similarly before the treatment is applied, then why is the red line so much significantly higher than the black line?
Well, because it's the change it's how they change over time that has to be the same.
Oh, I see.
Okay?
Okay.
And that's actually one of the nice things about diff and diff is that it takes out the fact that, right, the control group might always, or the treatment group might always just be higher than the treatment, or the treatment's always higher than control. That doesn't matter. The only thing that we're assuming is that when they move, they would have moved the same.
Okay.
Okay?
Okay.
So now what I'm going to do is I'm actually going to define a double difference, no, a triple difference, that we're going to use to back out what happens to the treatment group. And it's a lot of differencing is what you can see here how we're differencing A out of B. So one of the differences we're going to use, I should have like pictures, but I don't want to pull the board up, is we're going to look inside and outside of a buffer drawn around the house, or drawn around the well. So if you're outside of 2,000 meters from a well, we're going to say that in general you're not probably getting hit with any of the lease payments, which are good, or like the disamenities of the thing like potentially contaminating your water or giving bad air quality because you're far enough away. So outside of 2,000 meters and inside of 2,000 meters, all the houses are both getting hit with like the increased price of smoothies, right? Because they're high just everywhere now because there's lots of well workers living there. But only the houses inside 2,000 meters are getting hit with bad smells, you know, light pollution, noise pollution, stuff like that. All right, that's probably a conservative assumption because probably at 2,500 meters you're still getting hit with some of those things, but we're gonna, that would only make the estimate we're gonna get smaller, okay? So the second thing we're gonna assume, sorry, kind of go out of order. just realizing these slides are a little bit kind of mixed up. Let me just say what the second thing is. The second thing is we're going to look at houses that have groundwater and houses that have piped water. Okay, so in your mind, have two wells, all right, and draw a 2,000 meter circle around each one, and look inside and outside of the 2,000 meter circle. As you go inside the circle, you're getting all the disamenities associated with being close to a well, relative to outside, which has none of the disamenities, but has like the increased house prices because everybody wants to live there. Now what we're going to do is compare the change going from outside to inside the circle across places with groundwater and places with piped water. Okay? So if it's all about lease payments, then going from outside to inside the circle should make the price go up. Because now all of a sudden you're getting paid lots of money. So that should also be true for a groundwater house, because they're getting paid lots of money in lease payments. But some of that increase might get diminished by the fact that now they're scared that their water source is going to go away. So if I compare the change from outside to inside the buffer across a place with piped water to groundwater, the thing I'm going to net out is the fear of the groundwater contamination. That's the part that like gets left over when you difference across those two differences. Yeah.
So for this, you're assuming that all the house buyers know whether or not they have piped versus groundwater, and they know like the effects of whether.
Well, really, what we're trying to estimate is what do house buyers perceive about the risk.
Okay.
And it's possible that they're overestimating the risk, but we're just measuring this is what housing markets say the risk is. Okay? We kind of do assume, well, they do know where their water comes from. Yeah. And they do know if there's a well there. It's pretty easy to see. So the last thing we're going to do, and this was the thing that actually turns out to make a huge amount of difference, is that we're going to limit the, so we're already talking about inside and outside the buffer, piped water, groundwater. We're also going to use house fixed effects, like because we just talked about them being important. And what I don't want to do, this is a picture of a county in Pennsylvania. This is a city in the county in blue. This is the rural countryside out there in white. It's very wrong in a lot of ways to compare a house that's in the middle of, you know, this small city in Washington County, Pennsylvania, with a guy living out in the middle of the woods, because even if you have house fixed effects, the dynamics, the changes in prices in the city are very different from the way prices change out in the woods. So what we're going to do is take a 2,000 meter buffer around the very edge of the city. And the city is where the water comes from piped water, and the countryside is where it's groundwater. We take this 2,000 meter buffer and we're going to throw out all the houses inside it and outside of it, and only consider the houses on that band, right? And if you think about it, if you've ever lived in or been in a place that has like piped water and groundwater, there's a buffer, there's like a line you can draw between the city and the countryside. And the houses along that line are about as similar as you can get, except some have groundwater and some have piped water. Okay? What I don't want to do is compare a small little cabin in the woods with groundwater to a small little house on Main Street with piped water, because they're very different. So along this boundary, I've got piped and ground, but they're basically in the same neighborhood. Okay? So we're going to do all of these things to the data, all of these differencing, and we're going to throw away like 99% of our data and only look at that buffer. Okay? And yeah, probably what I'll do is I'll just show you these results, and then we'll finish up on Wednesday with this. Oh, and the other thing, on Wednesday I want to do the in-class experiment on housing values, which kind of shows you how things get capitalized into house values, kind of using, it's kind of like doing the tradable permits exercise, but it might not be as elaborate. We're going to do it in just this room. What that'll mean is we may only get a quick start on travel costs. So who's my travel cost group? Who else? Okay, one more probably, right? Yeah. Are you travel costs?
Ohio.
Yeah, it's Ohio. So that might mean that we don't really cover travel costs in a lot of detail till a week from today, if we do that on Wednesday. I'm happy to sit down with you guys at any point you want between now and then, like this afternoon or tomorrow, if you wanted to go over the travel cost methods so you could start the project, but if you wanted to wait until next Monday, you could do that too. I was hoping to get it all in this week so there wouldn't be much difference, but I do want to do this exercise on Wednesday. Okay, so just let me know if you guys want to get started earlier. Okay, so here's what happens if you just look at raw data, and I think this is really compelling. This is basically the house price with like the attributes of the house pulled out. You run a regression first on house attributes, and you take all the coefficients, and you take the residuals from that regression and plot them. This is the price before they drill the well. Okay, so it's taking all the houses that are within a buffer around where a well is going to be drilled, and you plot them, and this is the price before it's drilled, and then the dotted line is the price after. You can actually see inside 2,000 meters, the price goes up after drilling, which is, and this is for piped water houses, okay? Which indicates these guys are actually getting lease payments. Here's what happens when you do it with groundwater houses, okay? Here's the house price sales, given how far away they are from where the well is going to be drilled, and here they are after the well is drilled. So the prices drop a lot, like after the drilling happens, right? When you're close. So when you're close enough that you're actually potentially worried that this is going to contaminate your groundwater or your drinking water supply. So here's the actual numbers. If you do this difference in difference estimation, the band means we're using the area between the city and the countryside versus the full data set. You can see we drop our sample a lot when we throw away all the houses in the city and out in the countryside. So you've got your effect on all the houses within 2 kilometers. This is sort of the effect on everybody, whether you're piped or ground. And you can see that it's generally positive, and it gets all the way up to about a 10% improvement in house value when you use all the controls possible, fixed effects, double differencing, and you use the narrow band around the piped water area. But if it's a groundwater house, you have to add this additional coefficient to it, and this is a huge negative number in hedonics world, minus 26%. So if you're a groundwater house, you get a 10% bump up and a 26% bump down, so a negative 15% impact, okay, by having one more well pad within 2 kilometers of your house. So the key thing to keep in mind, because it's not that easy to interpret, you have to think about this. This is all relative to everything that's happening outside of 2 kilometers, right? And outside of 2 kilometers, smoothie prices just went from like $3 to $18, which means like all the house prices might have gone up because everybody wants to live there. Relative to all the prices going up, if you live inside 2 kilometers, your price goes up even more if you're piped water, but it goes down by 15% if you're groundwater, relative to what's happening elsewhere in Pennsylvania. So this has been used in court cases before in Pennsylvania for zoning arguments. And you have to explain to attorneys for Range Resources, because they try to like catch you on this over and over again. You have to explain it a million times. That what we're measuring is everything relative to something that is not in the model. It's been differenced out, everything else that's happening. And they'll say, well, we talk to realtors who say prices are skyrocketing in Pennsylvania. That's probably true. They are going up in Pennsylvania. But relative to the going up prices, if you're on groundwater, the prices are actually going down. Okay, relative to the going up, which means that people are afraid of groundwater getting contaminated. That's the point of the exercise. Okay, groundwater contamination is something housing markets worry about. So if you're a regulator in Pennsylvania, you may actually want to spend some money to require these guys to use better concrete on their downpipes, because that would be the thing that would prevent contamination down the road. Okay, or you'd argue maybe people have no idea what they're talking about. The average house buyer knows nothing, and this is just fear. And that was actually Range Resources' main argument against these results. Okay? But there's some wisdom to the market, right? Or at least that's the way we usually think about it. People tend to know something, and at least